Hello everyone, this is the explanation video for homework 4. Now, in homework 4 we will have two basic topics. First of them is this quarter car model, which you can see here in figure 1. Now, this is a model of a vehicle, but it's the quarter car model of the vehicle, which corresponds to the one of the tires and then the quarter body of the vehicle. We use this system in order to analyze the system's suspension and the road performance of a vehicle. Now, here we have basically the road surface, and if this is basically aligned, if there's no height difference, then we have a smooth, nice road on which we test basically the vehicle. But of course we will apply some interesting road models here. For this homework we've just constrained it to just a simple one, but usually we have road models which we use here and then test the vehicle on those realistic road models basically. Now, since this is the road, it touches the tire. This is basically the tire model. We will have a mass spring damper system that molds the tire. Because it is an elastic material, we need the spring and damper in order to give basically the tire feel here. So it's a basic model to model a tire. Of course, this is not the most realistic one, but it is used commonly, so we've also opted for that. And then, of course, we have the vehicle body. And when you as a driver sit in a vehicle or as a passenger, you are in the body and you will experience all the forces that will apply to the body here. And then again, we have here the suspension between the tire and the vehicle body. But again, the model is not that complicated. We have mass spring dampers for that. But then again, we have this actuator here. And if we design a control law, which is basically the aim of this first part, then it is called the active suspension part, which tries to isolate the vehicle body from the road surface. So it's basically a disturbance rejection problem. And if we don't design any control, if this is open loop basically in terms of control, then this is basically called the passive suspension. Now, this model is widely used, and you can search the internet. You will just directly find this figure 2. So if you are willing to get more information, you can just Google the internet. You will basically find whatever you need. But we will focus on the disturbance rejection problem, which is not a reference tracking problem as usual. We will use the state space model here, given here. We also have the values here. And using the state space model, it is possible to come up with some interesting controls. First of all, we have a special controller, this one here, and basically the states of this state space model is the position of the upper body, the position of the tire, their derivatives, because that is velocity, and that's basically it. We have 4 states for that. The first controller that we will look at is going to be a special one, especially designed for this quarter car model. And it's just a scalar, like a p-type controller, if you wish. Of course, calling this a p-type controller is not correct. Maybe we should call it something else because of the derivative here. But you can see k is a scalar. It's not the state feedback controller. It is just a special single scalar controller. Which is applied very specifically, as you can see. Now this is the control law. Here is the model of the system. So we will use these in conjunction to come up with a stability analysis for the scalar. Because we have a system, we need to examine its stability. And then we have a coefficient, a single coefficient. So this reminds us, of course, of the root locus. So you should come up with the positive and negative root locus. and then conclude what the stability interval is for this gain k. After you've done that, we've given you an interval, but of course there is no stability involved here. So our parameter will not exceed 10 to the power of 3 in terms of magnitude, and we've just put in the signs there. But if you have a stability, you will take the intersection of these two intervals, of course. So we didn't give away what the stability interval is, but minus 1000 and 1000 will be basically the upper bound on the coefficient here. So in terms of practicality, it's not infinity, basically, it's limited. But we ask you to minimize the amplification of the closed loop system. Since you know the interval, you can just take the controller and obtain the closed loop system. And we have a special type of road input, which is 0.3 sine 2 pi t. So at this frequency, we want you to minimize the amplification of the closed loop system of the disturbance. That's basically what we want from you, and obtain a controller gain, of course. So you should basically use the interval, try all points between or in the interval, look for the amplification at the frequency that is given here, and try to minimize it. So up to this point, we've basically come up with a controller. Now what we want you to do is to design a state feedback controller that assigns the closed loop poles to the same poles. But of course, here we say that you should use the Ackermann formula, but you should keep in mind that we don't want you to use the MATLAB ready commands. We want you to go through the steps of the Ackermann formula, which is the controllability matrix, the inverse of that, then the desired polynomial, PDS, and then the conversion to PDA, and then using the Ackermann formula to obtain the controller. That is what we want here. So this is basically symbolic toolbox here that I'm talking about, not the ready place commands or Acker commands or something that helps you in just one line. That's not the aim here. You should provide the necessary steps. And of course, we're looking for the state feedback controller that assigns to the exact same poles that you have obtained here in the closed loop. So that's that. And of course, compare the controllers and the results and comment on the results. That's basically necessary at this point. Now, once we've done that, we focus on the state feedback controller. But now we want to optimize basically the state feedback controller, but we don't know the relation between the poles and the disturbance rejection. So what we can do is we can just use genetic algorithm, just the default stuff, or GA in MATLAB, and minimize the amplification of the closed loop at the frequency. So basically we repeat the question here, the second question here, but we have a state feedback controller. We don't know what the bounds are in terms of stability, so we're going to search it with the genetic algorithm. And we are trying to come up with basically a very good controller that minimizes the amplification or the effects of basically the road here. By the way, why do we need to optimize our controllers or our system's acceleration? Because this is acceleration here, what we are trying to minimize. Here we have the acceleration as the output, the upper body acceleration in this direction here. It is important because if you're a passenger or driver in this vehicle, you will experience this acceleration, and in terms of comfort, this is discomforting. If the road gets messed up quite much, then this is discomforting, so you should basically try to optimize that. Or if you are in the logistics, if you're carrying fragile things, basically goods, then this acceleration should also be minimized because they are fragile. So basically these two are the aspects that we aim for. Therefore we try to minimize or isolate the vehicle body from the road as much as possible. That's done by minimizing the amplification of the disturbance, basically. So this is a disturbance rejection problem, and we try to use a special controller. First of all, we analyze the stability of that, and then we try to optimize that. Then we look for the state feedback controller that assigns to the exact same pulse, and we comment on that. After that, we design a state feedback controller. Now we have more parameters. We have 4 parameters. So therefore, we need to search for all of them. We use GA for assistance here and try to minimize the amplification of the disturbance again. Then, of course, you are going to compare this special controller design here, because it's a special controller, and the state feedback controller, which is optimized via GA, because these are the only optimal controllers. You're going to compare them in terms of body magnitude plots, pole spreads, etc. So you obtain the state feedback controller, you compare them. That's basically it. After that, since this is a quarter car model, we want you to discuss the ride comfort, drive safety, which I've talked about. These aspects in terms of industrial and practical aspects of both the design methods. So we have a controller that looks like this, and we have the state feedback controller. We want you to talk about what you think in terms of the industrial or practical aspects in terms of ride comfort and drive safety. But you should, of course, base your arguments based on the plots that you've obtained here. So that's an important thing. But of course, keep it simple, like 4 or 5 arguments. Just 1 sentence per argument is good. So we don't want you to write a whole page about it. Just 4 or 5 arguments, that would be enough. So this is basically the first part. We have a quarter car model. We're looking for a special controller and a state feedback controller. We optimize them, we compare them, and there's stuff about it. Now we have the second part, which again is about a vehicle. But think about this as the suspension part of the vehicle, and this may be about the speed dynamics or the position control of an electric car or vehicle. Now we have a transfer function here, but the transfer function is between the velocity and the velocity reference, so they are not basically the same. We have a input. If we give a certain acceleration, a velocity input or speed input, then we get this speed. So this is a vref v transfer function. But we want to use this model with the internal dynamics are modeled. We have everything ready. The only thing that we are interested in is position control. So of course this is a vref transfer function. We would like to have this position velocity reference in terms of the plant model. This is not the entire plant model, therefore. But you can obtain the plant from here. We want to prevent overshoot, and we want to use 10 seconds of settling time for step type references for the position control. So basically, you know what this means. You know where the poles should be. We are looking for position control. Now, first of all, you have to obtain the position plant, because this is not the position plant. And then you are going to convert this position plant into the state space model using the controllable canonical form. You can just Google it or look at your lecture notes. You will immediately recognize what this is, and use that in order to convert this into state space. So again, we are not looking for MATLAB commands, so don't use them. We are looking for the steps. So you should basically give the controllable canonical form, define the parameters, and then define the controllable canonical form of this. Now then, this is a more basic example. You are going to design a state feedback controller that does the job given here, position control without overshoot, 10 seconds of settling time. And of course, you are asked to design the Lindbergh observer and provide the necessary steps. Provide the necessary steps here and here. Then we want you to take the observer, the state feedback controller, the car model, and implement them using Simulink. You should apply bandwidth limited noise, which is directly a Simulink block, to the output of the position. when you measure the position, there will be noise basically, and we want you to apply bandwidth limited white noise with signal power 1. This is just a simulating thing. And then you are going to use that noisy output in order to be a bit more realistic in terms of application of the system. So plot the step response with a position reference of 1000 meters, the estimated states, the system states, the position, the speed, everything that would be necessary, comment on the results. So actually at this point, what we want to see in this simulink model is this electrical car model, which is this transfer function here. Of course, some additional stuff for the position plant maybe, but we want you to have a transfer function up here, but then you generate the output with noise, you take the measurement, then you have the observer, then the state feedback controller, then you generate the input and apply it to the system. In that case, of course, you will not be able to look for the system states and the observer states and compare them. So what you should do basically at this point is maybe use another simulink model where you just compare the states of the whole system, where you have two state space models probably, and compare the states only. And in your final answer, where you provide basically the necessary stuff from here, you use the transfer function here. So we want to see this transfer function in the resulting simulink model, but if you need, you can just use inner copy, convert everything into state space and compare them. Okay, so why do I force you to use the transfer function? Because then it would make sense why we use the observer. Of course it should work, so validate that using another simulink model, but here in the final image I want you to have a transfer function up here, some additional stuff here, band limited white noise and stuff, and then the output, observer, then the state feedback controller connected to each other, and then that is generating our input signal. So that's basically it. We have an extra question here for those who are interested. This is not this is an optional one, and if you do this and if you do it correctly, you will get extra 10 points. And it goes like the following. Since we have an observer state feedback structure, we want you to obtain the transfer function of that. Now usually it takes the output of the system and generates the input of the system, or rather the input that is going to be applied to the system and the output of the system under control. Now when you are obtaining the transfer function of that structure, the input and output will be reversed, of course. Your input will be Y, which is the output of the system, and you're generating the input of the system, but that's your output. So keep that in mind, and if you wish, if you want to look for this question, you can directly try to come up with a transfer function that consists of the observer plus state feedback structure. And that's basically it. Of course, the report that you're going to create, the presentation that you're going to create matters in terms of quality and stuff. But there are basically two questions. One of them is disturbance rejection using state space models, and the same for reference tracking. Now, all the rules, all the previous rules from homework 3 apply for homework 4. You will again work in teams. You can, if you are happy with your previous team, you can maybe apply to this homework with the same team, but you should basically create your team for homework 4 again, and you can just use the same teammates, but you should apply to the homework with the new team. Other than that, well, yeah, everything is the same. Again, we will look for some personal reports and stuff. Yeah, that's it basically.